Guys, my name is Mackenzie Poncell, and this is my presentation for Physics 2211 Lab 1 on the momentum principle. In this lab, we will discuss how Newton's fundamental laws of physics can be observed in the real world. According to the first law of motion, an object in motion will stay in motion until acted on by an unbalanced force. The second law, also known as the momentum principle, states that a net force causes a change in momentum. However, if there is no net force, the momentum is constant. If there was no friction under ideal conditions, then an object with an initial velocity would continue with that same velocity. This experiment uses Python to create a computational model of the motion of an object in the real world. This is done by using a motion tracking software to determine that the object has a constant velocity, and then this will be compared to the experimental values determined by the code. So for our calculations, we use the velocity update formula, which is Vf equals Vi plus Fnet over m times delta t. And you can see to the right here how we implement into our code. Below that, you can see the position update formula, which is Rf equals Ri plus Vf delta t. And then also here's the formula in the code. To solve for the initial velocity, we use the change in position over the change in time. We use the first two position points in our data and divide that by the corresponding time, which is final minus initial. When we do this, we get an initial velocity of negative 1.6667 meters per second. Okay, here we have Tracker. It is our motion tracking software. We have defined the origin of our chart to be the ball's center of mass while it has an initial velocity. We're starting at frame 60 and we'll end at frame 105. You can see the ball's motion here, and it corresponds with the position versus time chart on the right. You can see that it has a negative sloping velocity. As the ball moves, it also corresponds with our data points here, which is our time, and our x, which is our position. And that goes all the way to our final time of 1.501, with our final position being negative 2.448. Here we have our glow script code written in Python. We start with defining some initial conditions and properties. Our ball's mass is 0.34 kilograms. The initial position is a vector with negative 0.328 in the x component. And then our initial velocity is that number that we found in the calculation slide. It's negative 1.6667 in the x component. We have our time starts at 0, and our delta t is 0.033. In the calculation loop, we have our while loop to run until our final time, which is 1.501. We have our net force set to 0 because we have a no net force interaction. Here we have the velocity update formula and the position update formula. After all of this is run, we see that the ball's motion extends in the negative x direction, and it correlates with a position versus time graph with a negative slope. Velocity is constant as seen here. And then we have all of our data points printed out. This is the Excel spreadsheet we're going to use to compare the experiment position and the model position. In column C, we have all the times from both the experiment and the computational model, starting from 0 all the way down, as you can see. In column D, we have the experiment position given from Tracker. That's until row 47. In column E, we have the model position given from the glow script code. That's all the way down to here, lining up with the last of the glow script time. Then in the chart, we can see that we have a position versus time graph where the experiment position and the model position are very close. They're both linear with r squared values of 1. However, there is some deviation towards the end, which is due to a number of factors. So after looking at GlowScript, Tracker, and Excel, we noticed that the object moved at a near constant velocity when given an initial velocity, and was under no net force interaction. The predicted velocity from the object was faster than the actual velocity of the object. This is to be expected since the prediction ran under ideal conditions of no friction. Other factors, such as the texture of the ball or the wind, could have caused the ball to have the change in velocity towards the end. The lines of best fit were deviated slightly because of these unideal conditions, even though the R-squared values were the same for each. So what if we were to change the orientation of the axes? I currently have my axes defined where the ball moves in the negative x direction with a negative velocity. By flipping the axes, my velocity would become positive, but still stay the same. The slope of my line would also become positive. If the orientation of the axes were flipped, this would result in a position versus time graph looking similar to this right here, where the positive x direction is to the left and the negative x is to the right. This results in a positive slope. Because we know that the object moves with a constant velocity, there must be no net forces. However, we're not able to know all of the individual forces acting on the ball to determine this net force because we observe the system of force as a whole.